Okay, so picking up exactly where we left off last time, we were starting on the binomial and the Bernoulli distribution and random variables in general, right? So I want to kind of review the binomial a little bit and go further than we got last time with the binomial, and then also in parallel with that be discussing more about random variables, okay? So here's the binomial, just to remind you. Binomial distribution is one of the most famous distributions and one of the most useful ones in all of statistics. And we write it as distribution. We write it as bin of NP for shorthand. It has two parameters, n and p. That's what they're usually called. I mean, you could call them whatever you want, but the default choice would be to call them n and p. So those are called parameters. If you change the parameters, then you have a different distribution. It's still called a binomial distribution. So strictly speaking, there is not just one binomial distribution. There's a whole family of binomial distributions because you can let n is any positive integer, p is any real number between 0 and 1. So for any n and p, then we have a binomial NP distribution. Well, what is that distribution? Well, there's actually three important ways to think of it, and all three are important as far as we're concerned in this course. So the first one, I think, is the most important because that's the story, and the story tells us why do we care about the binomial. If we didn't have a useful story for it, then there's no point in looking at it. So the story, as I mentioned last time, so just reviewing last time, we have n independent trials. Each trial results in success or failure, and this is just the distribution of the number of successes. Okay? And in notation, we would write x. This notation means that x is a random variable that has this distribution. What does it mean to say that it has this distribution? Well, it means that we can interpret it in any of the three ways that we're about to do. So the first one I just mentioned, it's think of x as the number of successes in n independent. That's a crucial fact, is that the trials are independent. Bernoulli P trials. And Bernoulli P trials is what I just said. Each one is success or failure, where P is the probability of success. So that's the probability of success. So you can define success however you want. You can define success to be failure and failure to be success if you want. Everything will still work. The key is that every trial results in success or failure, but not both. But other than that, you can define success however you want. So that's just a generic word. So for example, the most famous example of a binomial would be flipping a coin n times, and you could define success to be the coin landing heads and failure to be the coin landing tails, or you could define it the other way around. But either way, this is counting successes, however you define successes. Okay, so a lot of times you'll see binomials explained in terms of coin flips just because it's easy to talk about that, but I think you can, we'll see many examples later in the course, but I think just you can already see that this is a very general setting, right? You have n independent trials, and then you count the number of successes, and you can define success to be whatever you want. So this is a very general, useful distribution. Okay, the second way to think of a binomial is in terms of what are called indicator random variables, sum of indicator random variables. And this I didn't write out last time, but it's actually just immediate from the story, which is that we can think of x as x1 plus x2 plus blah, blah, blah plus xn, where xj is 1 if the jth trial is a success, 0 otherwise. So that's called an indicator random variable, and we'll be using them a lot. It's called an indicator because it's just indicating, was the jth trial successful or failure? One indicates success, 0 indicates failure, right? So it's just a very simple encoding. Success is 1, failure is 0. Okay, so then if you think about it, what I wrote here as an equation is exactly the same thing as what I wrote in words here, because This just says add 1 every time there's a success, add 0 if there's a failure. So that's just how we count, right? If I want to count to 5, I would go 1, 2, 3, 4, 5. If I added 1 5 times to just count the number of successes. So this is very, very simple. I'm just doing 1 plus 1 plus 1 each time there's a success. But it can actually be subtle, and it's actually very, very useful to think of it this way. Because what we've done is broken down somewhat complicated distribution into very, very simple, a sum of very, very simple things that are just 0 or 1. So that's useful. And the xj's are independent. X1 through xn, I'll introduce one more acronym now, our IID Bernoulli P. The acronym IID is used a lot in statistics, so you may as well define that now. IID means independent and identically distributed. So what that means is, because we assume that the trials are independent, and these are the indicators of success for each trial, so those should be independent. That's what independent means. Identically distributed means all of these x's have the same distribution. In other words, they're all Bernoulli P, and remember from last time, a Bernoulli P is just means 1 with probability P and 0 with probability 1 minus P. So the key, a very, very common confusion is to confuse random variables with distributions. The random variable is, mathematically it's a function like we were defining it last time, but intuitively, this is just x1 is 1 if the first trial is a success and 0 otherwise, right? So that depends on the first trial. The distribution is saying what are the probabilities that x will behave in different ways. So you can have lots and lots of random variables that all have the same distribution, because the distribution is saying what's the probability that we'll do this, what's the probability that we'll do that, okay? But they're not the same random variable. They're independent, but they all have the same distribution, Bernoulli P. Okay, so that's what IID means. So all this is saying is just decompose the number of successes as add 1 every time you have a success, okay? And then the third way, which we also mentioned briefly last time, is to write down the PMF. I'll talk more about PMFs today, but I introduced it briefly last time. That's the probability mass function, and all that is just saying what's the probability that x takes on any particular value. And last time we showed that for the binomial, that's n choose k, p to the k, q to the n minus k, where q equals 1 minus p. Because if we have n trials with exactly k successes, then that's the probability for one specific way to do that, and then that's the number of ways to choose where the successes are. Okay, so we can immediately derive the PMF. So that's called the PMF. But let me go over here and talk a little more generally, what's a PMF, what's a distribution. So we usually abbreviate random variable to RV because we use them so much. It's nice to have a shorthand for that. So just to remind you from last time, what is it? If we have our sample space S, and if we think of that in the Pebble world interpretation, then that would be the finite, the case where there's finitely many. There's some pebbles. Okay, and I drew them as open circles just in case I feel like writing numbers inside of them. But this is our sample space. There are different possible outcomes. A random variable is a function that assigns a number to each pebble. So if we could think of it as like 7, 7, 5. I'm just making up some numbers. 7, 7, 5, 5, 3, 3, 3. You put whatever numbers you want. I kind of lined them up so that within each column they have the same number, but it doesn't have to be that way at all. I mean, I drew a very simple example because that's something I can draw easily on the board. The sample space could be this incredibly complicated, possibly infinite space that you could never draw. It could be very high dimensional, infinite, whatever. But the picture is each pebble gets assigned a number, okay? So we're starting with this abstract space of possible outcomes, and then we're assigning a numerical value to each one. That's what a random variable means. So if we talk about x equals 7, for example, where x is a random variable, and we have to think, what does that mean? That's an event. Remember, an event is a subset of the sample space. So in my picture, that event would consist of these two pebbles that I labeled 7. So it doesn't matter what the numbers are. I don't know if the numbers are easy to see. I called these two 7, these are 5s, and these are 3s. But you can put whatever numbers you want. X equals 7, what does that mean? That's not like an equation that you solve in some way. You know, it looks strange the first time you see it because that's a function, that's a number, and what are we really saying here? We're not saying try to solve that equation. We're not saying it's a constant function. What we're saying is that that's just notation for an event. What event is it? Well, it's the event that x equaled 7, right? Which is those two pebbles in this picture. Okay, so that's an event. So therefore, it makes sense to write down things like, we're going to find something called a CDF. So x equals 7, or x equals any little x is an event. X less than or equal to little x is an event. So it makes sense to talk about its probability. So we could write p of, so if we let f of x, f of little x equals the probability that x is less than or equal to little x, then this function, capital F, is called the CDF of x. And that stands for cumulative distribution function. That's too many letters to write. So that's why we call it CDF. So let me explain what this function means. Why is this function important? So I'm just letting x be any random variable right now. So the sample space could be infinite, could be much more complicated than this. You can use that picture for intuition. But we could have some incredibly complicated sample space. A random variable is whatever the outcome of the experiment is, the random variable assigns some numerical value, right? So x less than or equal to little x is an event that either, right, before you do the experiment, you don't know what x is. After you do the experiment, maybe you observe x happened to equal 7, and then if this little x happened to equal 9, then we'd say, okay, this event occurred because 7 is less than 9. That's all it means. So that's an event. So this is saying, as a function of little x, the probability of this event, that's called the CDF, and that's just one way to describe the distribution, okay? It's not the only way. There's other ways to describe a distribution, but this is one way that, in principle, determines all possible probabilities about x. So if later we wanted to know what's the probability that x is between 1 and 3 or between 5 and 9, we'll do some examples like that next time. But the idea is, as long as we know this function, capital F, we could answer questions like that. What's the probability that x does this? What's the probability that x does that? All of those questions could be answered in terms of this. So CDF is a way to describe the distribution because it's telling us the probabilities of different possible values for x. And let's talk more about the PMF, probability mass function. This is only for discrete random variables. So I have to tell you what the difference is between a discrete random variable and a continuous random variable. Discrete means, for our purposes, usually we can just think of it as meaning that it takes integer values. Like a binomial is discrete because the possible values are 0, 1, 2, 3, up to n, right? Integers. But in general, it means that the possible values, they don't actually have to be integers, but it has to be something you could list. Maybe a finite list, maybe an infinite list. So our A1, A2, A3, etc. that you could list out. This list might end, with AN, or it could go on forever. Well, I'll list both of those cases, AN, or it can go on forever, A1, A2, etc. So you could list out the possible values of the random variable. A continuous random variable would be, there's a little more to it than that, but it would be the case where we could take on any real number or any real number in some interval, that kind of thing. There are random variables that are neither discrete nor continuous either. You can kind of have a hybrid of discrete and continuous. But if we understand discrete and continuous, then you can handle those hybrids as well. So we'll mainly be looking at discrete and continuous random variables, and we'll start out mostly by doing discrete, and then later in the semester we'll be doing more continuous, but we'll still be using discrete as well. Okay, so that's what a discrete random variable is. And once we have that, we can say, what's the PMF? The PMF is just the probability that x equals aj for all j. So to say what's the PMF, you have to say for example, if these a1 through an are just, the integers 1 to n, it says to say what the PMF is, we have to say what's the probability that x equals 1, what's the probability that x equals 2, and so on. We have to specify all of those probabilities. So clearly that has to satisfy two things. Let's call this Pj. So Pj is the probability that x equals aj. So we're specifying, right? That's why I called this last time like a blueprint for x. This is saying what are the probabilities that x will take on certain values. That's describing the randomness of x. So what does Pj have to satisfy? Well, of course, Pj has to be greater than or equal to 0, because it's a probability. And the other condition we need is that the sum over all j of Pj equals 1. Because if the sum is greater than 1, well, that doesn't make sense. If the sum is less than 1, then it seems like we haven't listed out all the values, right? Because x has to do something, okay? And I'm assuming that this is a complete list of the possibilities. So this just says x has to equal something, so the sum has to equal 1. So these are the two conditions you need for a PMF. And if you wanted to go the other way around, you could say, pick any numbers Pj satisfying this, and then that would define a valid PMF. So these are the conditions for when is a PMF actually valid. So this is for discrete random variables. Usually, it's much easier to use the PMF than the CDF. The reason we need CDFs is that it's more general. That this definition works for any random variable. This only helps us in the discrete case. Right now, we're focusing on the discrete case, so we can mostly be doing PMFs. So if you had a problem where I said, find the distribution, what that means is either give the CDF or, if it's discrete, give the PMF. Either way. Usually the PMF is going to be easier. But those are equally valid ways to describe the distribution. Okay. So coming back to the binomial, let's just check that this is a valid PMF that I wrote down. I should have written that this is for k between 0 and n, an integer. And this is 0 otherwise, because these are the only possible values. Okay, so is this valid? Well, first of all, this is greater than or equal to 0. That's obvious. So the only thing we have to check is that this adds up to 1. And in fact, if we add up sum k equals 0 to n choose k, p to the k, q to the n minus k, how do we know that's 1? What does this sum remind you of? It reminds you of the binomial theorem, hopefully, that this looks exactly like the binomial theorem. By the binomial theorem, that's just p plus q to the n. But p plus q is 1, because q is 1 minus p. So that's 1 to the n equals 1 by the binomial theorem. So by the binomial theorem, the sum of the binomial PMF is 1. That's why it's called the binomial distribution, because it's connected to the binomial theorem in this way. So that was easy to check. And If somehow this sum is not equal to 1, then there's something seriously messed up, right? Because it has to equal something. So the PMF has to add up to 1. So that would mean that this equation was wrong, but this helped to check, okay, that's comforting, it adds up to 1, that makes sense. Okay? So that's the binomial. Now let me come back to the thing that I did at the end last time. With the sum of two binomials, okay? And let's actually see why that's true from all three of these perspectives. First one I already did last time, but I'll remind you because it's very quick. X is binomial NP, Y is binomial MP, and they're independent, and we want to show that the sum is binomial N plus MP. Okay, so that's what we did at the very end last time, but I want to show you different ways of seeing this. That's what we're trying to show. And before we can actually say more about it, I should make sure everyone is clear on what does x plus y actually mean. We're adding two, mathematically speaking, we're adding two functions. The way you add two functions is the sum of two functions. They have to have the same domain, and in this case, the domain of both of them is Pebble World. Okay. Now, if you have two functions with the same domain and you want to add them, what do you do? Well, you just compute both functions, and then you add the values, and then that's your new function. So the sum of two functions is defined as compute both functions and add them. So therefore, this makes perfect sense. I can add up random variables as long as all our random variables are on the same sample space S. It makes perfect sense to add them, multiply them, square them, cube them, whatever we want, right? We could take, e to the power of this thing cubed if we want, for whatever reason. That's a random variable, right? How would you compute that random variable? Well, you observe before you do the experiment, you don't know what it's going to be. After you do the experiment, you know x and y take on certain values, and then you just compute the function. And so you have a new random variable. So that's all we're doing. Intuitively, this is the number of successes in n trials. This is the number of successes in m trials. And these are separate sets of trials because I said they're independent. So this would be like flip the coin n times and then flip the coin m additional times. So we have a total of n plus m coin flips or trials. Notice it's the same p for both. This will not work if this one is like 1/2 and this one's 1/3, okay? But I assume p is the same for both, so we have n plus m trials. Each trial has probability of success p. And so what's the number of successes? Well, just add up this number of successes plus this number of successes. That's the number of successes, so it's binomial n plus mp. Okay, so that's what I did at the end of last time. That's just immediate from the story. We don't have to write any algebra or anything like that. But I think it's helpful to also see how would this work from this perspective and from this perspective, which we didn't do last time. So from the second point of view, let's say we wrote x as x1 plus blah, blah, blah plus xn. And if we write y equals y1 plus blah, blah, blah plus ym, where all of these x's, xj's and yj's are all independent Bernoulli p random variables. Then x plus y equals, well, it's the sum of the x's plus the sum of the y's. That's all. Okay, I didn't do very much with that. I just this plus this. Okay. Now all we have to do is recognize what's the form this is in. This is just a sum of n plus m independent Bernoulli p, right? So that's a sum of n plus m IID independent identically distributed Bernoulli p's. But according to this, if we take a sum of n in IID Bernoulli p's, that's a binomial NP. And here there's n plus m of them. So therefore we have binomial n plus m p. So this method is also easy because we're just adding up IID Bernoullis with the same p, so it's binomial. There just isn't anything more to it than that, because they're all independent. It would get more complicated if they're not independent. All right, now for the third way, we have to actually do a calculation. But it's a useful calculation to see. So the third way would be use the PMF. So I want to show that x plus y is binomial by computing its PMF. So what I need to do is compute the probability that x plus y is some number k. And if this is of the same, binomial form, then we'll say, okay, it's a binomial. And if not, then something's wrong somewhere because we have a contradiction. All right, so how do we do that? Well, this x plus y, it doesn't seem too obvious how to deal with it, unless using this way or this way. Those ways make it easy. But if you're not thinking in those terms, it just sounds like we've added two random variables. That sounds like it could be something complicated. In fact, in statistics, this is called a convolution, and I don't think it's a coincidence that convolution and convoluted both sound very similar. So we have to do this convolution. How do we do a we've never studied convolutions in this class. I mean, we will come back to convolutions later in the semester, but at this point, it's just convolution. What's that? Well, so this is, same strategy though, right? Wishful thinking. What do we wish that we knew? Well, I think this would be easier if I knew the value of x. If you want, you can also assume you know the value of y, either way. Okay? But let's condition on x. You can condition on y if you like that more. Let's condition on x, because this would be a lot easier if we knew the value of x. So that suggests use the law of total probability, where we condition on x. So we know that this is the probability that x plus y equals k given x equals j times the probability that x equals j. Summed over j goes from 0 to n, but actually, let's just sum up to k, because if the sum is equal to k, there's no way that one of them, x on its own, could not be greater than k, because you're adding up two non-negative things. So we could sum up to k. Now, let's just compute this. This is the sum j equals 0 to k of the probability. Okay, so x plus y equals k given x equals j. That's useful information, right? We can plug in x equals j and rewrite that for y. This says y equals k minus j. Notice it's still given x equals j, so we'll have to deal with this. Times the probability that x equals j, well, that's just immediate because x is binomial, so I'm just going to write down the binomial PMF. It's n choose j, p to the j, q to the n minus j. Now, the key fact here is that x and y are independent. Independent, I haven't written out the formal definition of independence for random variables yet, but if you understand independence for events, then you understand it for random variables, which is just that knowing that this event occurred, x equals something. Independent means that if we know x, it gives us no information whatsoever about y. So if we know that x equals j, that tells us nothing about y. So independence means we can just cross this out. That's by independence. So it's just the probability that y equals k minus j, because the definition of independence is that conditioning on x gives us no information about y. Okay, so now this thing in front is just the binomial PMF again. Y equals k minus j. So that's just going to be m choose, there were m trials for y. M choose k minus j, p to the k minus j, q to the m minus k plus j, times the stuff we already had there, n choose j, p to the j, q to the n minus j. Okay, well that looks ugly, but we can simplify it at least a little bit. We can collect the powers of p, so that's p to the k p to the k does not depend on j, so we can take it out of the sum. It's a constant. Collect the q's, m minus k plus j, and that's n minus j. So we have m plus n minus k. The j's cancel. So that's also a constant. That comes out. So that's q to the m plus n minus k times whatever is left over is this sum, j equals 0 to k. M choose k minus j, n choose j. Well, that looks pretty ugly. But does this sum look familiar to anyone? Yeah? Vandermonde. Very good. This thing is what we called the Vandermonde. You don't have to memorize that this thing is called Vandermonde, but when we were doing story proofs, this is exactly one that we looked at, a sum that looks like this. It looks like a complicated sum, but using a story, it's actually easy to evaluate this, and that's called the Vandermonde identity. And the Vandermonde identity says that this will just equal m plus n choose k. So this equals, sorry, I'm going right to left here. Vandermonde says that this equals m plus n choose k. So that was the Vandermonde identity we did last time. Not last time, but we did it a while ago using a story proof. Okay? So that's m plus n choose k according to the Vandermonde thing we did, and that means, well, now that looks exactly like the binomial n plus m p PMF. Okay? So that's true. So obviously this was a much more complicated and difficult way to do it, especially if we didn't know or didn't remember how to do this sum, then we'd be stuck at this point. Luckily, we already did the Vandermonde earlier, so I can just quote that result. But even with this, it was still a lot more work. And without this, then you'd just be left with this hideous sum. Okay? But it still worked, so we would have a contradiction. So another point of view of what we just did is that we actually just proved Vandermonde again, right? Because if this were not equal, we'd have a contradiction. Therefore, that this identity, this has to equal m plus n choose k, otherwise we have a contradiction. So that's our second proof of Vandermonde's identity. All right, so that's the binomial distribution. We'll be seeing a lot more with it. And I want to kind of contrast that with a common mistake is kind of thinking that things are binomial when they're not. So I want to give like kind of a simple example to about, that you should be careful about that. The key assumption, sorry, these boards are so squeaky. The key assumption is that the trials are independent and they all have the same probability of success, okay? So if the probabilities of success are different, we can't say it's binomial, and if they're not independent, we can't say it's binomial. So let's do an example that's not a binomial, yet a common mistake would be to somehow think that this is binomial. So here's just a simple example to think about with cards. And suppose we have a random 5-card hand from a standard 52-card deck, okay? And we want to know what's the distribution. Find the distribution of the number of aces in the hand, right? So we pick a random subset, 5 cards out of 52, all subsets of size 5 equally likely, and the number of aces that, there's some number, possibly 0 of aces in that hand. We want to know what's its distribution. And so as I said before, when we say find the distribution, we could find the CDF, but it's going to be easier to work with the PMF. This is certainly discrete, because the number of aces is either 0, 1, 2, 3, or 4. So this is a discrete problem, so it's going to be easier to find the PMF. I'll say PMF or CDF, because finding the CDF would be equally valid. It would just be more complicated, so let's just do the PMF. Okay? So how do we do that? So let's let x equal the number of aces. That's our random variable. And this kind of notation, on the one hand, it's very intuitive, right? I'm just saying, let's look at the number of aces, right? So it's very intuitive. On the other hand, sometimes students kind of struggle with, how do I interpret this as a function, right? you're not, most students are used to writing like f of x equals x cubed, that's a function. So it's worth thinking through, why is this actually a function? Well, it's a function from the sample space to integers between 0 and 4. It's a lot easier to write it out this way than to write out some other type of equation for it, but it is still a function. Okay, so let's find its PMF. So we need to find what's the probability that x equals k. First of all, so that's what we need to find. Well, first of all, this is obviously 0, except if k is 0, 1, 2, 3, or 4, right? You're not going to observe 2.5 aces or 5 aces if it's a standard deck, right? It's not possible. So those are the only possibilities. And for a lot of these problems, it's helpful just starting by listing out or describing what are the possible values, okay? Because a common mistake with probability is to list some PMF where either it doesn't sum to 1 or it involves impossible values or things like that. Okay, so those are the possible values. That's just obvious. There's 4 aces in the deck, right? Okay. So we can actually immediately conclude that the distribution is not binomial because we can think of each card as being a trial, but those trials are not independent, right? Because if the first 2 cards are aces, or if the first card's an ace, it's less likely that the second card is an ace, and the more aces you have in the earlier cards you're dealt, it's less likely to have more. In an extreme case, if the first 4 cards you get dealt are aces, then the 5th card is definitely not an ace. So the trials are not independent, it's not binomial. But let's just find the PMF just by thinking about it. What's the probability that x equals k? Not because we memorized anything, but just by thinking about it. So we can go back to the naive definition of probability because I said all 5-card hands are equally likely. So there's 52 choose 5 possible hands, equally likely. So we're using the naive definition. Now we want to know what's the probability that the number of aces is equal to k. Well, there's 4 aces in the deck, and we need to choose k of those aces. There are 48 non-aces, and we need to choose, if we have k aces and 5 cards, we have 5 minus k non-aces. So that's for k between 0 and 4. So that's just the multiplication rule, naive definition. Kind of has a neat pattern, which is that 4 plus 48 is 52, 5 plus k plus 5 minus k is 5. Well, it's kind of nice looking. All right, so that's the answer. But that's not the whole end of the problem yet, because I want to try to check whether this actually makes sense and try to see how does this relate to other stuff. First of all, does this probability remind anyone of anything that we've seen before? Yep. It reminds you of the Vandermonde. Yep, it's very reminiscent of the Vandermonde, which, kind of looks like, well, it is this, and this kind of looks like that. Okay, we'll come back to that point. Anything else that reminds you of from the homework? Yep. The elk problem. This is like the elk problem. Why do you say it's like the elk problem? Yeah. Right. Okay, that's a great observation, that this looks exactly like the elk problem. Now, it's not just some coincidence that it happened to be like somehow you memorized the answer to the elk problem and you see it kind of looks like that. What you saw is there's actually a connection there, which is that you have these 2 groups. So if you remember the elk problem, I'm not expecting you to memorize the answer to the elk problem, okay? But you should remember the story of the elk problem, which was that there's a population of elk. Some of them are tagged, some of them are untagged. You collect a sample, and you want to know what's the probability that that sample has exactly K tagged elk. That was the problem. Okay? So you don't have to memorize the answer to that, but the problem is a useful one to think about. This is exactly the same. Instead of elk, we have cards. Tagged, so instead of tagging elk, we're tagging cards as aces. Now, what does it mean to tag a card as an ace? Well, it means it has an ace written on it. The cards are tagged already, right? 4 of the cards are tagged as aces. The other 48 are not tagged as aces. So we have 4 tagged cards, we have 48 untagged cards, where tagged means an ace. Okay? So it's the exact same thing. So it's not just like, it's same as. Okay? So that's a key sort of thing that you should be thinking about in this course is trying, when we do one problem and see how it relates to other problems, it's exactly the same. Okay, now coming back to the comment that this reminds you of Vandermonde, let's actually write this out in a more general version. Suppose that we have, let's say we have a jar full of marbles, and let's say B of them are black and W of them are white marbles. Okay. You pick let's say n of them, pick random sample. Simple random sample means that all subsets of that size are equally likely of size, let's say, n. Okay, so then the question is, what's the distribution of the number of white marbles in the sample? Number of white marbles in the sample. Notice again, that's exactly the same as the elk problem and the ace problem, where we're thinking, instead of thinking of tagged and untagged, we're thinking of white and black, but it's just the same problem. Okay, so we can immediately write down the answer. The answer, let's call this x. Okay, that's our random variable. So we want to find the probability that x equals some number k, and we can immediately write down the answer because it's the same thing. We have a sample that we have B plus W marbles. Let's say W plus B marbles, of which we choose n. And now, how is it possible that exactly k are white? Well, we must select exactly k are white. That means we need to choose k out of the white marbles, and however many it is left, if there's k white and we have a sample size n, there must be n minus k black marbles. So that's B here. And let's just for emphasis write down where is this what are the constraints here? Well, first of all, it must be true that 0 is less than or equal to k, less than or equal to w, because we couldn't possibly have more white marbles than there exist white marbles. Similarly, we must have 0 less than or equal n minus k less than or equal to b. But remember, we did take the convention that if k is greater than w, we take this to be 0. So this is just for emphasis. Okay? This distribution is called the hypergeometric. So if we say hypergeometric distribution, you should immediately think back to the elk problem, and you should be thinking of this. The hypergeometric distribution is defined by this story, or equivalently by the elk's story. That's the name of the distribution. This is its PMF, but it's if you just memorize the PMF, that's not going to help you to recognize when you should apply this distribution. So the key thing is to understand the story of the hypergeometric, which we now have 3 versions of, and we'll see more later. Now, so that's not a binomial, because you could say, like, even if you, I mean, I was imagining grabbing the marbles all at once, but if you want, you can imagine picking one at a time. The key is that it's without replacement, right? You're sampling without replacement here. If you picked a marble and put it back and put it back, and then you wanted the distribution for the number of white marbles, that would be binomial. Because if you replace it each time, then you've just reset things and it's independent. But if you're sampling without replacement, then the trials are not independent, so we do not get a binomial. So it's without replacement. So that's a key distinction between hypergeometric and binomial. And already from that, we intuitively, we have an intuitive connection between the hypergeometric and the binomial, which is that binomial, as I said, if you put the marble back each time, pick one, put it back, pick one, put it back, that'll be a binomial for the distribution of the number of white marbles. Hypergeometric, if you don't do replacement, that tells us something important, which is that suppose that the number of marbles is like 1 billion, and suppose that our sample is very small compared to 1 billion, let's say 10, okay? Now, if we're picking 10 marbles out of 1 billion, it's extremely unlikely that we would pick the same marble more than once. So it must be that sampling with replacement and without replacement should behave very similarly there. And mathematically, you know, we can derive those kinds of things, but intuitively, under conditions like that, where with replacement and without replacement don't have much difference, then the hypergeometric should be approximately binomial. All right. Now, there's one other thing we need to do with the hypergeometric, which is to check that this is a valid PMF, right? So first of all, this is non-negative, okay? Secondly, we need to show that this sums to 1. So if we sum this up over all possible k, so let's say we sum k equals 0 to w, w choose k, b choose n minus k, divided by w plus b choose n. The w plus b choose n is a constant, so that just comes out. That comes out in the denominator. And I'll put 1 times this. Then you can put it in the denominator. I created a denominator for it. Okay, so you can take this out over in the denominator. I'll put 1 over 1. Now I have a denominator to stick this in. Now what's left is this sum here. Well, this sum should look very familiar. That's the Vandermonde again. And in fact, that Vandermonde is w plus b choose n, which is what we took out. Therefore, we immediately get 1, again by Vandermonde. So that's consistent on the one hand. On the other hand, we can think of that as a proof of Vandermonde, because if that didn't work, then it would be a contradiction. Therefore, we proved Vandermonde for the 3rd time. All right? So this, you know, that's the hypergeometric distribution. Okay. One last thing, just to talk a little bit more about CDFs. I just want to draw a picture of what a CDF might look like. So CDF, remember that's the probability that x is less than or equal to little x. Now it could look a continuous one. I'm just going to draw a continuous one and a discrete one, and we'll talk more about these next time, but just to have a picture in mind. Continuous one might look like this, where notice if x is like, you know, negative 1 billion, like if you let x be more and more negative, it gets less and less likely that x is less than or equal, right? So it's going to approach 0 this way. So imagine you have a function where here's 1, here's 0, and we have a function it's increasing, okay, because as you increase little x, it's more and more likely that this event occurs. So you might have a function, this is just an example, but it helps to have a picture in mind of what a CDF looks like. So I'm drawing something that is continuous, and it approaches 1 as you go this way. It approaches 0 if you go this way, and it's increasing like that. Okay, so we'll see a lot more like that later. But just to have a quick picture of a discrete one, it could look like it's going to have jumps. Okay, because for example, let's assume x takes possible values 0, 1, 2, or 3, or something like that. Well, then at 0, it's going to jump like that. And then at 1, here's 1, 2, 3. And then it's going to jump again. So maybe it jumps to, say, there. And it's going to be flat, and then it's going to jump, and then it's going to jump. Let's say it jumped like that. And then it stays at 1 forever. And I'm drawing open circles there because it takes the higher value at each one because I define this as less than or equal. So this is 1 again. So this would be a CDF of a random variable that has values 0, 1, 2, 3. And, oh, it jumped. Let's see. Oh, it jumped at 2. So this one actually is, I would need one more jump. Anyway, so this one's actually 0, 1, or 2. Okay? And then the probability is 1 that it's less than or equal to 2. So for in the discrete case, you have these complicated jumpy functions. It's easier to use the PMF. In the continuous case, it's often useful to use the CDF. All right, so that's all for today.